Hello, my name is José Antonio López Díaz. I'm a physicist, mathematician, and generally fond of science. And today I will present a new, I expect it's a rather new approach to the introduction to the special relativity theory of Albert Einstein. I mean, what you will see here, I haven't seen in any of the usual books of introduction to general relativity theory. So, in a sense, it can be a novel approach to you. The starting point of this talk will be imagine a thought experiment when in the line of Einstein we introduced this type of mind exercise. We imagine something. Imagine a scientific who lived before Einstein, let's say 100 years before. There were many great scientists, physicists, mathematicians, and others. And imagine how could this scientist before Einstein, before electromagnetism was discovered, how could he have speculated about the structure of space-time using, let's say, rather evident hypothesis about the structure of space and time. So let's begin with the basic frame of what is called a Minkowski diagram. Minkowski diagram, who of course appeared after Einstein published in 1905 his paper on Introduction to Special Relativity. But this is a tool that I will use along this talk. We imagine that we have only one spatial dimension. Space has of course three dimensions, but we concentrate here also on a line, one dimension, one spatial dimension, which is drawn here, the x-axis, and we have the other dimension, the time. We will play with these both dimensions. And the first thing we have to be very clear about is that the basic points in this diagram are the so-called events. So let me draw an event here, N, which will be a point, and events are usually noted by capital letters. This is event P. And this event has something of an absolute character. By absolute, I mean that all the observers that we will consider will have to be very clear about this event, what it is. P is only a name. It is not the coordinates of P. So P is an event. In this case, it will have, for this observer O, called it O, the origin of the axis, also we use the same letter for both. The observer O will assign to this event. In this case, these are like Cartesian coordinates. We'll assign the x and the coordinates. In this case, this is x, this is t. Well, all this should be pretty familiar to all of you. And then we will ask ourselves about how other observers will see this event. We will restrain ourselves to a particular kind of observers. All observers, other observers we will consider, will agree on this origin event. For all of them will live, so to speak, in this event, the so-called 0, 0, 0 event. I mean, other observers will move with a constant relative velocity, like this one. This is an event length. Another observer, let's call it O prime, and this other observer is going along this trajectory, where this is the relative velocity. That means that this is the unit of time, or this has to be the relative velocity v between both of these observers. And we will ask ourselves how this O prime observer moves, you see, with the uniform speed relative to O, as we see here, how these things. And we will be considering here, it's also important to remark, all these observers are what are called in classical mechanics Galilean observers. I mean, they are not accelerated. They move with constant speed relative to one another, and that none of them is experiencing any acceleration. Then our scientists will say, okay, we know that time is absolute. That was the classical frame. Time is absolute means that if this observer, the O observer, has this line here parallel to this one, along this line we have all events have the same time, one unit of time. The same, this line means the time is 0, here time is 1, and both of these lines are the same for O and O prime, because I say time is absolute. But of course, space is not absolute in classical physics. And this O prime, at this point, is, first, his space axis here, the x-axis, is the same for both observers, because O prime also goes along this line. So here we draw the unit of length. So we can imagine that here we draw these coordinates. So this axis is the same for both x, right, equals x prime. But then here, this observer O prime, this is here, he starts to measure lengths from this point. So his unit of length has been displaced. This is the unit of length here. We have to draw a parallel here. This is the new unit of length here. Okay? Understand? We should this parallelogram. You can imagine that this is repeated. It covers all the plane. What this means, let's summarize, so to speak, this idea. We have the unit vectors, t-axis, x-axis for O, and then O prime has moved this t prime, this is t prime, and the unit vector of this axis t has been moved, but not so for the other unit vector on which both observers agree. Okay? Then, of course, this type of diagram emphasizes the basic asymmetry between the space of time that is typical of classical physics. We move one of the unit vectors, but not the other. The unit vectors agree, both of them. These spatial vectors. So, let's go on further a bit and imagine that this scientist goes to the limit of a very small relative velocity. So imagine that this is not a finite, so v, but an infinitesimal v. I will draw here. Differential of v, very small. We are tending here to the limit. And then he could ask himself or herself, okay, why not speculate with the possibility that the real change or an imaginary space-time you want, that this unit vector also moves. An infinitesimal magnitude, because for an infinitesimal change, for the velocity of changes have to be infinitesimal. He could also wonder why this movement has to be horizontal in this diagram, and not orthogonal to this axis? Why not this one? And here, this. So many possibilities. But let's introduce two considerations that allow us to restrain the range of possibilities here. First one is the isotropy of the space. Isotropy of space means that it has to be the same if you look to your right or if you look to your left. Or the physical transformations have to be the same. So physical symmetry, isotropy, means here that imagine we have this. Let me draw again this for clarity. Imagine that we have the transformation, an infinitesimal transformation like this, with this vector here, instead of horizontal. Isotropy would mean that this, of course, means that the velocity goes, this infinitesimal velocity goes to the right. This observer is moving to the right here, respective to O. What would happen if the velocity were directed to the left? Well, it's obvious from isotropy that the transformation would be the specular symmetry of this with respect to this axis. And we would have necessarily this other displacement. The same if we look to the right, we have this displacement. If we look to the left, and this axis, this would be just this symmetrical image of this one. But then, this poses a very serious problem to this type of transformation, because we have here, at this point, if we plot these transformations for different p's, we have here a function which is not smooth, it's not continuous, has not a definite tangent here. We cannot draw a tangent at this point because we have a key. We have a kick here. For a smooth curve, remember, the curve is smooth if the tangent directed to the right has to be to have the same slope as the tangent directed to the left. But this is not the case here. What we are supposing here is that we have this angle and here this angle and there is a kick. That means that this must be discarded. We do not want abrupt changes, not smooth functions. So for these changes to be smooth, which is of course a pretty natural requirement of space-time transformations, we have to postulate that all possible infinitesimal changes have to be like this one in classical physics. You have to go in the orthogonal here. And the same has to be said from possible transformations here. Imagine that we have on this unit vector along the x-axis, we have an infinitesimal change like this. Then reasoning like before, we apply symmetry, we will have for a transformation in the opposite infinitesimal velocity, we will have this one, but then this one is for this vector, which is the opposite of this one. So for this same vector, the change has to be the opposite of this, negative of this. So we have to go to this vector, and we counter the same problem as before, that this will not be smooth. So for both unit vectors, the infinitesimal transformation has to be along this orthogonal line. But that's a pretty important restriction of possible space-times or transformation, infinitesimal transformation of the space-time. And the second argument is that we can use the freedom that we have in the choice of units, of space-time units. Of course, if we have, for instance, we have this vector, there is no reason here why the modulus of the infinitesimal vector here has to be the same as this. But changing the units, either of space or of time, or maybe both, we can make that both lengths of these vectors are the same. So we are left with only two reasonable possibilities. For this change, the differential of V, we have this change here, the same as in classical physics, but speculating with this type of, let's call it imaginary at that time, space-times, we have only two choices here, either going upwards or downwards with the same length as here. Let's first examine what happens when the change would be going here downwards. So we go, this matter, we go here, we draw here this new x prime axis. But then we will use the so-called relativity principle. But I mean here not the Einsteinian relativity principle, but the Galilean invariance or relativity principle. So at that time it was not called, so far as I know, relativity principle. I mean, that principle, which is valid in classical physics, asserts that all reference systems that move one with respect to one another at uniform relative velocity have to have the same physical laws. Okay, that means that I can position myself in this new system and imagine a change of differential V with respect to this one. And according to what has been said, the change would be the same. We will have to go along the orthogonal here and the orthogonal here. Well, one can see that what we will have here, composing this way different infinitesimal changes, that we have the rotation of the axis. That defines simply a Euclidean, if you want, with rotation of the axis. Okay? But then the problem is that after we compose a number or integrate, if you want, these transformations, infinitesimal transformations, we end up, for instance, having a system whose T prime axis is along here, and as come here. But this type of system has a very big problem. We can go as all the events are reversed. The causality principle is broken with this type of system after all the events that are here are on this line, which is the temporal line for the initial system. This other system as simultaneous. All of them occur at a given T prime. Of course, that means that for this other observer, he would have at a given time access to all the past and the future of this other observer. And then that will bring us to the paradoxes of causality, illustrated by the example of what would happen if someone killed my grandfather, after traveling backwards in time, and of course, that would be a paradox. I wouldn't be here. So that's the problem. If this other observer has access to all the past and future at a given instant of this other, the O observer, that of course breaks all the rules. So this is clearly a physical possibility. That scientists would have to conclude that this is not possible, and then the only remaining possibility is that we change here and we change with both of these vectors concurring, so to speak. Okay? Then, of course, we may reason, okay, let's see where does this lead us? Let's follow on. Let's consider a change for this other observation by another differential of the velocity. Here we will have to move parallel to this axis here. So we move here, and here we move parallel to this axis. Okay. What we see immediately is that this possibility, this other possibility, which, by the way, this is the special relativity possibility. What happens according to our knowledge of physics? What happens in the real world? What happens in the real world is this. Suppose we know at present. And what is evident from this picture here is that the transformations are symmetrical with respect to this line, the bisector of this first quadrant. Everything here, you see, this is symmetric to this. We have made that so by our choice of units, and the changes, the infinitesimal changes, have also the same magnitude. Arrange the units to be solved. So, composing as many as we like these infinitesimal transformations, everything is symmetrical around this bisector. But this bisector, which it's important to note that it has arisen from these other two hypotheses, basic hypotheses that we have said about space-time. We have not postulated in this approach that there should be a line of symmetry. Line of symmetry appears. And this line of symmetry, what does it mean? This line of symmetry defines the velocity. Velocity, which would be this one, with this unit. The observer O, but that velocity, note that the unit vectors are here the same. So this is the unit vector of x. That means that this velocity, with this choice of units, this very special velocity, which I know by the universal letter we use for it, which is c equals 1 with this choice of units. Of course, you may have guessed that this is the light speed, which of course in natural units is not 1, it's 300,000 kilometers per second. But what is important to see, because for a diagram it would be very awkward to have a so big a c, because that would mean that this line, with other choice of units, will be very, very close here to the x-axis. We will get everything completely straight along this axis, every transformation. We will only see this part of the diagram, which is, of course, what happens in reality in classical physics. Because this C is so big in reality, we don't see the details of the transformation of this axis, because all of them are compressed here. But if we have other units of space-time, we would see this very symmetrical and nice picture. Okay? So, this is our first very big consequence, of which, of course, historically, I suppose you know that it was the other way around. What Einstein postulated is that there is speed, the velocity of light, which is constant for all observers. Of course, it has to be said that this speed, since everything is symmetrical, for another observer, whichever you want, imagine that this is finite. And the velocity of this ray, you would have, this observer would have to choose some time here and see where this line cuts. And you will have to divide in the units of space-time, which are not the same. The length, the geometrical length of the units in different observers is not the same. But anyway, you would have this ratio of this this space x prime divided by this time t prime is always 1, because all these triangles are by the symmetry of the construction. You get that all observers see this let's call observer, which is really a photon, the ray of light, with the same velocity. That is the invariance of velocity of this singular speed, yeah, for all observers. That's the basic of the transformation of space-time in special relativity. And we can go on and derive some of the main results of special relativity fairly easy with this type of diagram. First of all, we can derive easily the equation of these unit vectors, and symmetrical this one. This equation corresponds to this locus of points describes a hyperbola. And that is so because the infinitesimal equation, we can reason here using the symmetry that at a given point for this observer, the tangent here for this locus has to be parallel to the symmetrical point. The symmetrical has to be parallel to the x-axis of this observer, which we know is symmetrical with respect to the bisector line. That means that this angle is the same as this one, and what we get is that equation can be written something like, for instance, the derivative has to be equal to x divided by t. That's pretty immediate using this symmetry, and that means that t minus x. We integrate this and we get that t squared minus x squared equals a constant k. And this k we can read here at this point at the beginning. We have that t is 1 and x is null. That constant means this is 1. This is the equation of a hyperbola, which is one of the conic sections, so-called conic sections. The ellipses, the parabolae, and the cases. They are well known from the Keplerian orbits and so on. And let's derive. I will clear a bit here. Let's derive one of the main results, the time dilation. For the special relativity, there is a very, very clear argument, which using these Minkowski diagrams is very easy to see, which is the following. We draw start with our observer O, and we have the unit vectors like before. And we will take advantage again of an isotropy argument. We consider two observers. One goes to the right with velocity v, and the other goes symmetrically to the left with velocity, this is O prime. Okay? These two, let's imagine that what's the relative velocity between O2 prime and O prime? Well, O prime, which is the velocity of this other observer, has to choose a given point. It can be this one, and it has to draw a line. The axis here of this observer is, remember the geometry, everything is symmetric around this line. So this is alpha, angle alpha. The axis x second has the same angle alpha. This angle, we have said that it's the same alpha because both are symmetrical. And the x prime axis goes like this with the same alpha angle. We have this structure. So this observer, O prime, has to draw a line parallel to its x prime axis. O goes like this. That means that it chooses, O prime chooses a given time, instant of time, and as in its line of simultaneity, all this line means that for O prime is the same instant of time. And thus, where is O second times? It is here, at this length. This is my time, and this is my length. So the quotient between this and this is the relative velocity between both. So let's imagine that this time length is 1 for O second, simplify matters. This has to be then the relative velocity. Let's call it, not to use the same letter B, let's call it U. U is the relative velocity between O second and O prime. Okay? And then, at a given instant, this instant of time for O prime, for O second, the time that has passed is only this. It's only this. This time, let's call it P. This is the time that has passed for O second. So, this means that what O prime sees as 1 unit of time, O second sees it only as P. We see here clearly that P is less than 1. P, by contraction, is less than 1. That means that while for O second only P units of time have passed, while for O prime it's been 1 unit of time here. So the time for O second seems to run slower as seen from O prime point of view. We have to be always very clear relativity from which reference system we are seeing things. So for O prime, we see that for O second, the clock runs slower. So this is the time dilation. Phenomenon that occurs in special relativity. And we can derive from here the following relation. This line here, parallel to this line, looking at the angles here, forms here a 90 degrees angle. So it's orthogonal. Has to be orthogonal because this angle is the same by construction. This line is orthogonal to this because both of these angles are alpha. That means that we can derive from here easily, which is P. I call P is use Pythagoras theorem. So the shrinking factor for time is this quantity. I will restore here natural units. If C had not been 1, we have to write it this way. Well, the general rule when working with a specific choice of units, like here, making C equal 1, and restoring natural units just to use C to make equations dimensionally coherent. And here we have 1 has no dimensions, so B quantity here has to be dimensionless. The only way to using C make it dimensionless is to divide it by C. That's the easy rule to restore natural units, which are the ones we can fly. Okay. Well, this is by definition gamma of B. Gamma of B is defined to be 1 over 1. Okay? This factor, gamma of B, as you see defined here, is always greater or equal to 1. It is 1 for the case of b equals 0, but it is always greater and can grow to infinity as b nears c. So this shrinking factor can go to infinity. This is the dilation of time, and quite symmetrically, we can see the very related law of the contraction of lengths. The contraction of lengths means that, imagine that we have here a given length, imagine a train or something, or a post here marking this length. Now we'll go to the other important relativistic phenomenon, which is called the length contraction. And with this type of diagram, and with this choice of units, the analysis is completely symmetrical to the one we have just made about time dilation. Let's imagine that we have here on the x-axis of the O observer an object of length L, big L, okay? So-called also relativity proper length, because it is on the reference system where it is with null velocity, okay? Then this other observer, here O2 prime, how much length will he see for this object? Well, of course, he's moving. The object is stable here, and we have to be clear on what we can mean by the definition of a length of a moving object. And well, the definition is pretty evident. We have to take a given instant of time in our reference of system, and let's imagine we make a photograph of the object and we measure the length. So what is important here is that we have to choose a given simultaneity in our reference system in order to define the length. It has to be at a given time, of course. We cannot measure the length of one of the ends of the object at one time and of the other at another time, because here the velocity enters. No, it has to be at one time. So this system has these lines, x2 prime, are simultaneities of O2 prime, okay? So let's go to one of the simultaneities, and this object here, since it is here on the O system, describes, this is one end of our object, describes this line, so-called in relativity weld line. The weld line means that goes here in the system, and the other end goes, of course, parallel. This object is at any time here. Remains here. So the length for O2 prime will be this segment here. Let's call it Q, and measure in its own units. It's got this geometrical length. We have to take account of the fact that the unit of length here is not the same as here, the same as of time. We have here this hyperbole, meaning that the units are changing in length. Okay. But if we look at this figure, this is exactly the same as we will see if we did it with time. If we analyze this observer and this one, we know that by dilation of time, we know the ratio between two times. And we see that this triangle is exactly similar to this one. So, what we arrive at is that it is again this gamma of the factor that is the key for this ratio of lengths. between the two systems. And we arrive here at a contraction of lengths. That means that if Q is, as I said before, the length in the prime system, Q over N, the ratio of lengths, is again 1 over gamma of V. So time dilation, length contraction are completely, let's say, symmetrical effects of relativistic laws of the space-time. Okay, with this, I will finish this exposition. We have seen the basics of the Minkowski diagrams. We have derived drawing of the basic properties of space-time, known, of course, before Einstein, known in classical mechanics, basically the isotropy of space and the Galilean relativity. In this case, we have now called the relativity of space-time, which both of these have allowed us to derive the acceptable transformations of these unit vectors apart from the one that characterizes classical space-time transformations. Remember, it's this one. The only other possibility, reasonable possibility, after a choice of units, an adequate choice of units, is this one, which is completely symmetrical around the bisector line of the first quadrant. This bisector defines a singular velocity, so-called c. This velocity is the same for all observers because of the symmetry. And we have also derived perhaps the two best known effects of general relativity very easily with these Minkowski diagrams. First, the time dilation, and very closely related with, symmetrically related with the length contraction. And, well, I will finish simply by making some reflections. We can ask ourselves, then, why, if this is, let's say, not so complicated, why didn't anyone before, let's say, Einstein, Lorentz, Poincaré, all these men, great science men, contributed to special relativity development, why didn't anyone come up with something like this, a theory like this? Well, first of all, I think we have to take into account that our space and time common sense notions are very deeply ingrained in our minds. As Kant said, our perceptions are all framed by space and time. And this space of time are the common sense space of time notions that we all live in our daily lives. And I would say that especially time has a very special meaning for us. This time is the same as the time of our conscience, the time we are aware of. And in a sense, it's a very strange idea to us, to think that the time flow of different observers can be dependent on the relative speed. After all, we as a species have to thrive on communication between ourselves. As a Homo sapiens, we know from evolution it was our key advantage was communication. We used our intelligence, but intelligence, our findings, our discoveries grew up, let's say, exponentially, thanks to the communication. Communication and empathy are basic to us. And that means, empathy means that it's very difficult to imagine that someone, because he is traveling or she is traveling with given velocity with respect to me, very great velocity has to be. Anyway, the flow of time for him or her is different as for mine. And I believe this psychological barrier also, that's my opinion, also played a role. If anyone had proposed this speculation that maybe space-time does this type of thing, probably all would have said, okay, that's a completely mad idea with no future. So, as other times in the history of science, it was other very important discoveries in physics, namely in this case the electromagnetic waves theory, electromagnetism in general, that gave rise to other questions that uncover the deep structure of light as waves, etc., as waves that transmit in the ether. At those times they spoke about the ether, and so on. And you know the rest of the history. You have the Vincent Morley experiments, the various of the speed of light, and so on. So, thank you.